Assalamualaikum warahmatullahi wabarakatuh dan salam sejahtera to all of you. Today we're going to learn on a new subchapter in basic element in process control, and we are now in week 4. In previous lesson, we had discussed on signal transmitter combination where the signal received from the sensor had been converted to the transmitter output whether in current, pneumatic or percentage. Transmit output was transferred to the controller for controller to make a decision. So in this week, we are going to learn on the control signal in basic element in process control. There are three principal types of transmission signal in process control industries. The pneumatic signal or air pressure normally range between 3 to 15 psig. The usual representation for pneumatic signal in process and instrumentation diagram is line with a slash. The electrical signals normally range between 4 to 20 mA or 1 to 5 volt. The usual representation for the signal in piping and instrumentation diagram is a series of dashed lines. The third type of signal is digital or discrete signal, which always represented by binary code of zeros and ones. The range of transmission signal can be found whether electronic, pneumatic, or percentage, as we discussed earlier. Every signal have their own minimum and maximum range. For example, for electronic, the range is from 4 to 20 mA and 1 to 5 volt. Pneumatic from 3 to 15 psig and 0.2 to 1 bar. And finally, the percentage is from 0 to 100%. If you notice, the transmission signal minimum value is different from one to another. In your opinion, why don't they start at 0? Okay, the most possible explanation would be signals are used to convey information. The signals from the transmitter to the controllers used by the transmitter to inform the controller of the value of the control variable. This signal is not a measurement in engineering units, but rather is an MA, PSIG, volt, or any other signal that is proportional to the measurement. The relationship to the measurement depends on the calibration of the sensor or transmitter. The controller uses its output signal to tell the final control element what to do. How much to open if it is valve, how fast to run if it is a variable speed pump, and so on. It is often necessary to change one type of signal into another. This is done by a transducer or converter. For example, there may be a need to change from an electrical signal in MA to a pneumatic signal in pound per square inch gauge, PSIG. This is done by the use of a current to pneumatic transducer as shown in the figure on the slide. The input signal may be 4 to 20 mA and the output signal would be 3 to 15 psig. The third element in basic component of process control is valve. Control valves are the most common final control element. They perform the action function of the control system by adjusting the flows that affect the control variable. In this chapter, we are going to learn on the most important aspect of control valve, the selection of their action and field position, the capacity and sizing, their flow characteristic, their gain and their transfer function, along with the different type of valve and their accessories. A control valve acts as a variable restriction in a process pipe. By changing its opening, it changes the resistance to flow and thus the flow itself. Throttling flow is what control valves are all about. The controller output signal position the valve, determining the valve position that in turn determines the degree of restriction to flow. Therefore, the controller output signal is the input to the valve and the flow is the output of the valve. In brief, the control valve purpose is to regulate flow of any phase, whether liquid, gas, fluid, and mixed phases that could possibly pass through it, and solid phase is by nature impossibly can. The control valve is used by more than 80% in the chemical process industries. The symbol for control valve is presented in the slide. Instrumentation schematic of control valve presented in the slide consists of the actuator and body. The actuator is means of adjusting the position of control valve, and the most common use of actuator is air pressure actuator. The air pressure actuator is the most common type found in industries due to its high reliability and low maintenance requirement of air. In this diagram, the controller signal represented in MT is in percent controller output as opposed to MA or PSIG. The actuator, as shown in figure B, converts the controller output MT into the valve position, which is VPT. The valve position is usually expressed as a fraction that varies between 0 and unity. As mentioned earlier, the valve position is usually expressed as a fraction that varies between 0 and unity. When the valve position is 0, the valve is closed and the flow is 0. On the other hand, when the valve position is unity, the valve is fully open and the flow is maximum. For a full range valve actuator, a 1% change in control output results in 0.01 change in fraction valve position. Most control valve use a full range actuator. In a real practice, there are possibilities when energy supply fails. As an engineer, what do you want the valve to do when the energy supply fails? This question concerns the fail position or action of the valve. So the main consideration as an engineer is safety. When the safest position of the valve is the closed position, the engineer must specify a fail close or FC close. Such a valve requires energy to open and is also called an air to open, which is ATO valve. The other possibility is a fail open, which is FO valve. Fail open valve require energy to close and are called air to close valve, which is ATC. There are two selections of direction of control valve that are ATO, which is air to open, and A to C, which is the air to close. Air to close or ATC or fail open used to allow flow of fluid during loss of pneumatic air supply. This action may save overheating or temperature related process such as catalyst heating or heating of polymerization process, whereby for air to open or fail close used to prevent flow when no pneumatic air supply. This action may prevent hazardous chemicals or flammable fluid from endangering life. To illustrate the selection of the action of control valve, let us consider the flash drum shown in the figure. Steam is condensed in a coil to partially vaporize the liquid feed and separate its component into vapor and liquid products. There are three valves in this example, one on the steam line to the coil and one on each of the liquid and vapor product. The valve on the liquid product controls the level in the tanks, and the valve on the vapor product controls the pressure in the tank. The question is, what we want each of these valves to do if the electrical power or air supply were to fail. As previously explained, each valve must move to its safest position when either the electric power or the air pressure fails. The safest position for the steam valve is closed, because this prevents a high steam flow that could vaporize all of the liquid and overheat the coil. Therefore, we select a fail close or air to open valve for the steam valve. For the liquid product valve, a fail close or air to open valve would keep the liquid stored in the tank. This action gives the operator time to shut down the feed to the tank and correct the cause of the failure. It is seldom safe for the liquid product to flow uncontrolled to the process downstream. Finally, a fail open or air to close valve on the vapor product line would allow the product to flow out of the tank and prevent the tank from pressurizing. It is important to realize that safety is the only consideration in selecting the action of the control valve. As we shall see in the next section, the action of the control valve directly affects the action of the feedback controller. The action of the valve determines the sign of the gain of the valve. An air to open valve has a positive gain, and air to close valve has a negative gain. This is easy to see from the following formula relating the valve position to the controller output. The valve position formula for air to open is equal to m divided by 100, whereas for air to close it's equal to 100 minus m divided by 100. These formulas relate the steady-state values of the variables. They do not consider the dynamic response of the actuator. Now, we try to solve this kind of exercise in order to find the valve position. If 10 psig is sent to the control valve, what is the valve position for air to close system and for air to open system? First, you need to convert the 10 psig to the percentage unit. So, in order to do that, we need to do the interpolation. From the interpolation, we will get the unit in percentage, which is equal to 58.3%. So to calculate the valve position for air to close system, the related equation is equal to 100 minus m divided by 100. So it will give you the valve position is equal to 0.417, whereas for an air to open system, the related equation is equal to m divided by 100. So valve position calculated is equal to 0.583. The CV coefficient, also known as flow coefficient of a control valve, depends on the valve position. It may vary from 0 when the valve is closed, valve position is equal to 0, to a maximum value, which is a CV max, when the valve is fully open. The variation in the CV allows the valve to continuously regulate the flow. The particular function relating the CV coefficient to the valve position is known as inherent valve characteristic. There are three common valve characteristics, which are quick opening, linear, and equal percentage. There are three types of valve characteristics which has been mentioned earlier, which are linear, equal percentage, and quick opening. Figure illustrated in the slide shows the condition of each valve characteristic. The differences can be seen from the shape of valve plug, where it's influenced the way fluid passes through the valve. The valve spindle allows the movement of fluid. Every valve characteristic have different behavior with respect to percent of full flow at constant pressure and percent of full valve stem travel. It can be seen from graph shown in the slide. What makes a control valve become linear, equal percentage, or quick opening control valve? It depends on the amount of flow produced with respect to steady increment in the stem travel. Now we go in details for every each of valve characteristic. The first characteristic is quick opening. As evident from its shape, the quick opening characteristic is not suitable for regulating flow because most of the variation in the valve coefficient takes place in the lower third of the valve travel. Very little variation in coefficient takes place for most of the valve travel. Quick opening valves are appropriate for relief valve and for on-off control system. Relief valve must allow a large flow as quickly as possible to prevent overpressuring of process vessel and other equipment. As we knew that quick opening is not suitable for regulating flow, However, this following valve characteristic, linear and equal percentage, is normally used to regulate flow. The function for linear characteristic as follows. The linear characteristic produces a coefficient proportional to the valve position. It is used when the process is linear and the pressure drop across the valve do not vary with flow. At 50% valve position, the flow through the valve is 50% of its maximum flow. The second type of valve characteristic that can be used to regulate flow is equal percentage. The function for equal percentage characteristic as given in the slide, where alpha is rangeability parameter having a value of 50 or 100, and 50 is the most common one. Produce an exponential function to the valve opening result in equal relative or percentage increment. It is used when the pressure drop across the valve do not vary with flow, and with process which the gain decreases when the flow through the valve increases. Exponential function has a property that equal increment is in valve position result in equal relative or percentage increment is the valve coefficient. When increasing the valve position by 1%, the flow increased by 1% of its value at the past valve position. Valve rangeability is also known as Tandem Ratio. It is a ratio of the maximum controllable flow to the minimum controllable flow. It is a measure of the width of operating flows that the valve can control. Common way to define the maximum and minimum flows at 95 and 5% valve position. The range ability can be calculated using this formula. Range ability is equal to flows at 95% valve position divided by flow at 5% valve position. If the pressure drop across the valve is independent of flow, the flow through the valve is proportional to its CV coefficient. We can calculate the valve rangeability from its inherent characteristic. For a linear characteristic, rangeability equals to 0.95, which is at maximum valve position, divided by 0.05, which is at minimum valve position, equal to 19. Whereas for equal percentage characteristic, the rangeability is equals to alpha to the power of minus 0.05 divided by alpha to the power of minus 0.95 equals to alpha to the power of 0.9. For alpha equals to 50, the rangeability is equal to 33.8. Whereas for alpha equals to 100, rangeability is equal to 63.1. For a quick opening characteristic, the rangeability is equals to 3. Thank you, and that's all for today. Thank you for your undivided